Hello students, welcome back to SapphireBlueChemspark. Let us start our today's session, coordination compounds from inorganic chemistry. The previous classes we completed introduction, Werner theory and the important terms to define the different parts of coordination compounds. Now let us see how a coordination compound is named according to IUPAC rules. While naming the complex compounds, first of all we have to identify whether the complex is homoleptic or heteroleptic. So the first condition we have to identify whether the complex is homo or heteroleptic complexes. Second point, you should identify whether it is a complex cation or complex anion. That also we have to identify, complex cation or complex anion. Third, we have to identify whether the complex it is with counterpart or it is simply the ion. Counterpart, that might be the simple ions of either cation or the anions, whatever may be. So first of all we have to look into the complex to identify homoleptic, heteroleptic. Why we are identifying homo or hetero? This is because the ligands to be named in an alphabetic order alone. So alphabetic order, if at all you have homoleptic, no need to worry about. You can go with their actual name. But in heteroleptic, there will be more than one type of ligand for which we have to follow the alphabetic order. Secondly, then the complex if at all cation, and the cation should be followed first of all. And if the complex is anion, if at all it is without counterpart, you can start with the anionic complexes. But if the complex is a neutral, that means a complex ion and the simple ions are there, always the name will be starting from cation followed by anion. So let us start the nomenclature of coordination compounds for mononuclear coordination entity. Mononuclear means the complex contains only one central metal ion. Such complexes are said to be mononuclear coordination entity. So the first thing we have to list out. What about the central metal ion? So suppose if at all polynuclear, we have to list out the entire central atom. It is now only the mononuclear. So let us identify what is the central atom of the coordination entity. Then the ligands, whether it is monodendate ligand or polydentate ligand, that we have to identify. Monodendate ligands, they can donate only one pairs of electron. Polydentate, they can donate more than one pair of electrons. So we have to identify in the coordination entity whether the metal ion is binding with monodendate or the polydentate. The coordination entity that may also have the abbreviated form of the ligands. Example, we can find ethane 1,2 diamine, that is shortly abbreviated as EN. Ethane 1,2 diamine, that was a very long name, so we can't, and its formula will be CH2, CH2, NH2, NH2. So such a long formula which cannot be given inside the entity. So such ligands, when it has the lengthy formula, that can be abbreviated like EN. Similarly, if we have oxalate, that can be given as OX. Or if we have triphenyl phosphine, that can be given like this. So some of the ligands, if at all difficult to predict its formula in the entity, for them we can able to follow the abbreviated forms of their formula. And If the ligand is a monoatomic, you can depict as such. For example, I can say Cl, Br like that, or even nitride like that I can give. If at all the ligand is polyatomic, for example, if I have NO3, it must be given in a parenthesis. So the monoatom, if at all the ligand is made up of a single atom, that can be given just like. If at all it is a polyatomic, the polyatomic to be given in the parenthesis. Then while you write the IUPAC name of coordination entity, no space would be given. So we have to start from the coordination number, the ligand, metal ion and its oxidation state. It is to be written without leaving any space. And if the charges of the ligands and the central metal ion, it has to be balanced. That what? It gives rise to the charge of the complex. So the ligand's charge and the metal ion charge to be balanced in order to get whether the complex is a neutral complex or a cationic complex or even an anionic complex. Then the coordination entity is always written with the charge carried by the central metal ion if at all the ligand is a neutral ligand. So neutral ligand, it has the charge 0, where the complex will have the charge of only the central metal ion. So in such cases, the coordination entity is to be written with a charge carried by the central metal ion when the ligand is neutral. So that's all how to write formula of coordination entity. The next one, rules for writing the IUPAC name. So here we just discussed about how to formulate mononuclear coordination entity. Now for this formulated one, we are going to write rules for writing its IUPAC name. Always, whether it is a simple salt or a complex salt, the name of the compound should always be started with cation followed by anion. This is rules. So first of all, I said you have to find out what type of complex is this, whether a cationic complex or anionic complex or a neutral complex. If at all cationic complex, you have to name first of all the entity followed by its counter ion. Or if the complex is anionic complex, then you have to follow the cation, simple cation followed by coordination entity. Or the complex itself a neutral, then you can go along with the normal path of giving their name. So the first thing we have to identify, we have to write cation should follow the anionic species, and when you start naming the entity, it has to start with this coordination number. In case of homoleptic complexes, the coordination number is nothing but how many group of atoms or ions there, that will make its coordination number. If at all heteroleptic complexes, you have to identify the individual ligands, how many times they bind with central metal ion. So while naming their coordination number, we have to make use of di, tri, tetra, penta, then hexa like that. These numbers only, the numerical prefixes are used such a way. Suppose if the ligand itself has any positions, that is the numerals, then for such ligands we are not supposed to give these numerals. Instead we will write for bi it has to be taken as bis, for tri it is to be taken as tris, for 5 it is taken as pentakis like that. So when the ligand as well as coordination number having the numeral, coordination number to be termed in terms of bis, tris, tetrakis, pentakis like that. If the ligand it doesn't have any position where we are using these numeral prefixes. The next one, how to name the complex. First of all, for the new anionic complex, we have to start with simple cation. After writing the simple cation, you should go with coordination number, finding out of homo or heteroleptic. Homoleptic, you can start simply with its coordination number followed by ligand. The ligands, whether it is negative or neutral or positive, that we have to identify. For the negative ligands, the metal should always end with. For the anionic complexes, I am saying if the ligands in the homoleptic complexes are only the negative, then the metal should always end with the suffix of ate. So, metalate will be given. Or in the case of cationic complexes where the metal as such it comes nickel, nickel only. But in the anionic complex nickel becomes nickelate. This is why we are identifying whether the complex is a cationic complex or the anionic complex, because both of these complexes they do differ in their naming of central metal ion. Then in the cationic complex, you can identify first of all coordination number followed by ligand central ion and its oxidation number followed by its counter ion. And the oxidation number must be given in Roman numeral. Okay. Then if at all neutral complex, nothing to worry. You have to go with their coordination number, name of the ligand followed by central metal ion with its oxidation state. That's all. Okay. Suppose if the oxidation state of the metal is 0, what you should write while writing the oxidation number? Yes, you have to take 0. That 0 it specifies the metal it is in its 0 oxidation state. So these are the different rules. Let us discuss some of the examples by applying these rules. Okay, let us discuss some of the examples now. Before naming a complex, we have to learn some more important informations regarding naming of the central metal ion or naming of the ligands depends on its charge as well as the abbreviated ligands. So let us find naming a central metal ion. The complexes may be a neutral or even a cationic complex or the anionic complex. This naming we are considering only for the anionic complexes. In the anionic complexes, the metal should always be ending with the suffix of ate. Example, if we say iron 2 chloride, we are saying FeCl2 as iron 2 chloride, or we will say ferrous chloride. So that ferrous is nothing but derived from its Latin name of ferrum. So some of the metals we have to get their Latin or the Greek name with its suffixes. Examples I have given. Iron, it is actually ferrum. So this is ferrate. And cuprum, it is copper. Cuprum to cuprate. Silver, silver is actually argentum. Argentum to argentate. Gold, aurum to aurate. Mercury, that is hydrargyrum to hydrargyrate. So such a way we have to name the complexes only for the anion. But in the cation, if you have iron 2 only you will write. Copper only, silver only. So the name change will be observed for this metal only in case of anionic complexes. Neutral and cationic complexes do not have such procedure. Let us go to the ligands. Ligands also we have positive ligands, negative ligands and neutral ligands. Positive ligands usually ending with the suffix of IUM. They used to say M. Okay. So yesterday we said some of the positively charged ligands NO plus, it is nitrosonium. So always the positively charged radicals have the suffix of IUM. This is said to be em suffix. So it is nitrosonium, or we can say NO2 plus, that is said to be nitronium. Okay, leave it off. Now let us go to neutral ligands. Neutral ligands are probably having one or more lone pair electrons on its atom. One of the atom will carry one or more lone pair electron, and they are capable of donating a pair of electron to the central metal ion. But these neutral ligands should have their specific name. For example, ammonia it is actually, but this ammonia is termed as amine in complexes. Suppose if one of the M you just removed off, that becomes amine. Amine is a different class of compound. Amine, that formula is NH2, but here we are taking ammonia. So to distinguish amine from ammonia, that M is included when we name the ammonia molecule as a ligand. So the spelling for ammonia is important. AMMINE, amine, you have to pronounce it. Then water. Water is also a neutral ligand, and it is named as aqua or aqua. So A or O, the last letter that may differ, no issues at all. And in carbon monoxide, it is named as carbonyl. Nitrosyl group, and this is nitric oxide, it is termed as nitrosyl. So in cases of ligands, the neutral ligand, they find their specific names considering their formula. The next one, anionic ligands. The neutral ligands have some special name. Similarly, anionic ligands should always be ending with the suffix of O. Usually, anions have the suffix of -ide, -ite and -ate. So these suffixes depends on the oxidation state of the non-metal present in the radicals. The ide is usually given for only the elemental form of anions. For example, oxide, sulfide, nitride, chloride. Here and all you may find only that element alone will have the negative charge. But in the case of ite and ate, you may find there would be a radical form of NO3 minus, NO2 minus, SO4 2 minus, SO3 2 minus, CO3 2 minus, such a way we will find. So whenever the element is with the oxygen having the negative charge, they will have the suffix of ite or ate. Depends on the oxidation state of nitrogen, halogen, sulfur, whatever it is. Okay, let us come to the point. Chloride, it is termed as chlorido. So E is dropped by O suffix. So the name is chlorido. So cyanido, chlorido, bromido, iodido, hydroxido, oxido, nitrido, such a way the negative ligands being named. Or if I have nitrate ligand, it is NO3 minus, the name of the radical is nitrate, where E is dropped by O. So the ligand is said to be nitrato. Similarly, nitrite I have, where E is dropped by O. So it is said to be nitrito. So this is how name the anionic ligands. Sulfate, sulfato, carbonate, carbonato. So such a way, if at all the ligands are negative, you should add the O suffix to the end of its name. Then abbreviated ligands. In abbreviated ligands, already I told, writing such a big formula in a parenthesis is not possible. So IUPAC recommended to make use of the abbreviated terms for certain ligands alone. Such ligands are ethane 1,2 diamine. It is represented as EN. This abbreviated form should always be given in parenthesis. Then oxalate. Oxalate is a negative ligand as well as a didentate ligand. It is didentate because two different donor sites it has. This is one COO minus, this is one COO minus. Both of the oxygen able to donate its electron pair. So it is a didentate ligand. And the other one is triphenyl phosphine. Phosphine is actually PH3, in which instead of the 3 hydrogen, phenyl group is present. So this is triphenyl phosphine. It is abbreviated as PPH thrice. I am sorry, the 3 will become here PPH3. So this is called triphenyl phosphine. Okay, we just discussed about neutral ligand, anionic ligand as well as abbreviated ligands. What about ambidentate ligands? Ambidentate ligands, we have NO2 minus or ONO minus. What we said, if the nitrogen is bonded to the central metal ion, then you should write the complex name at the end of the metal. You have to write nitrogen is attached. Such a way we will write N nitrito or nitrato, such a way which atom is bonded to the central metal ion, that atom should be given in its IUPAC name itself. Okay, let us take some examples to apply all these ideas in naming the compound. Let us take examples of one anionic complex, one cationic complex and one cationic anionic complexes. How to name the compound? So what we said, first of all the cation should follow the anion. So this is the case where the simple cation is potassium. So the name should be followed from cation to anion only. So the name it starts potassium. Okay. After naming the simple ion, now we are going to name the anionic complex. Before name the anionic complex, you have to balance the charges. No, this is 4K plus. So the charge of the complex will be 4 minus because of the counterpart. When you have the complex charge is 4 minus, then you should identify what is the oxidation state of central ion. Here the cyanide is the negative ligand and whose charge is -1. 6 into -1 -6, -6 that is equal to, we can write x minus 6 equal to -4 or x equal to +2. So the oxidation state of ion in this complex is 2. Okay, now let us start the naming of the coordination entity. Here first we have to take one coordination number. Then you have to go with ligand. Then you have to go to with the metal ion. After that you are going with oxidation state. This is what the root. So what is its coordination number? 6. For the 6 numeral prefix is hexa. So what I can take? Potassium hexa. Okay, hexa. And what is the type of ligand? Negative. Negative ligands will always end with the suffix of O. So it is cyanide. So the name is given hexacyanido. Okay. Then where we have to go? The metal ion. It is in anionic complex. Anionic complex always end with the suffix of ate. So this is iron. Its name is ferrum. So it is termed as ferrate. Then following its oxidation number 2, that is given in the parenthesis of 2. Roman numerical that always be enclosed in the parenthesis. The next one I am going to find. Here I have taken cationic complex because the complex is written first of all followed by the sulfate. So the first half of the name is always cation. So similarly the first one Potassium is the first part, simple cation. The complex becomes the second part. It makes the anionic complex. So similarly here, this is the cationic complex, this is the anion, simple anion. What we have to do? Always we have to name the cation followed by the anion. So here the cation itself the complex. So first thing what we have to do? Coordination number, then ligand, then metal followed by its oxidation number. I said it is the cation, and what is the charge of sulfate? Charge of sulfate is -2. Therefore, its counter charge of the cation will be +2. Now, the ligand is a neutral ligand. So, the charge of the ligand is 0. How many ligand I have? 4. So, 4 into 0, that is equal to 0 only. Now, what would be the oxidation state of metal? It is nothing but the charge carried by the complex becomes oxidation state of copper. This is only for the homoleptic complexes we are discussing, because in both the complexes you are finding only one type of ligand. So the +2 that becomes the oxidation state of central metal ion. How? X plus 0 equal to +2 or X equal to +2. That's all. Now let us name the complex first of all. How many? What is the coordination number? 4. 4 is tetra. So the first letter it starts with capital letter. So tetra. Amine, because ammonia is the neutral and it has its special name amine. So I am writing tetraamine. See, double M I have to write. Tetraamine. What is the metal? Copper. And it is the cationic complex. For cationic complex, you can write copper as such. So the name is tetraamine copper. What about its oxidation number? 2. So that is given in the Roman numeral, followed by its simple anion, that is sulfate. Over. Tetraamine copper to sulfate. That's all. Now let's go to the complex cation and complex anion. Whatever we discussed over here, going to apply here too. First thing what we have to do? Identifying the charges. Here cobalt cyanide is 6 times. It is -1, -6. Cobalt, it is actually N+3 state. So -6, -3. Here it is 0. So the oxidation state of chromium will be +3. So here it is +3. The some metal, they have their own specific oxidation states while they form their complexes. Based on that, I am taking cobalt in the +3 state and chromium in the +3 state. Now let us write the name. First of all, coordination number, ligand, metal, oxidation number. Once again, when you go here, coordination number, ligand, metal and oxidation number. Okay, let us start. 6. So it is hexa. The ligand is ammonia. So I can write amine, hexaamine. It is a positive complex. So it is chromium, hexaamine chromium. What about its oxidation state? 3. So chromium 3 followed by anion. It is once again the complex. So start with the coordination number 6. 6 is hexa. What is the ligand? Negative, cyanide. So the name is hexacyanido. And it is the negative ligand, negative complex. So the metal with the suffix of 8. So it becomes cobaltate. And whose oxidation state is 3. So cobaltate 3. That's all. Now let us name these complexes. In these complexes, you may find few of them are heteroleptic because they have more than one type of ligands. Find out this one. Platinum, En twice Cl2. En is an abbreviated ligand of ethane 1,2 diamine. And here 1,2 diamine I am writing. So let us start first of all. As it is heteroleptic complexes and it has no counter ion, so we have to find out first of all what about the oxidation state of platinum. Platinum, it is if I consider 0 because no counter ion I have. So En, it is a neutral ligand whose charge is 0. Chloride actually -1, its charge is -1. How many chloride I have? 2 chloride. So 2 into -1, that becomes -2. When I say the charge of the complex is 0, so the counter, the platinum must be in 2 state, +2 state. Okay. So let us start right. How to name the one? Alphabetic order, because it is a heteroleptic complex. It is chloride, it is ethane 1,2 diamine. So C follows the first one according to alphabetic. The C comes first. So we can write dichlorido, because how many times chloride is there? 2 times. So it is dichlorido. As it is negative, O suffix is given. Now we are going to name this one. What I said? If the ligand itself has any numerals, then the coordination number will be given in a different form. What is there? 2. 2 to be given as what I said? Bis. So what I am going to write? Dichlorido bis. This ethane, that is the En, to be written in the open bracket saying ethane 1,2 diamine closing the bracket. So here why I had taken bis? Because this ligand itself has that numeric value of di. That's why coordination number is given as bis. So dichlorido bis ethane 1,2 diamine. It is the neutral, so it ends with just metal with the oxidation state. So ethane 1,2 diamine, platinum 2. So here dichlorido bis ethane 1,2 diamine, platinum 2. That's all the name of the complex. Let us go here. Carbon monoxide is a neutral ligand, as well as these complexes are said to be carbonyl complexes. In all these carbonyl complexes, the metal is always exist in 0 oxidation state. Because of its the strength of the ligand, that and all we will discuss in our following sessions. So before that, you just remember, in any of the carbonyl complexes, the metal should always be in 0 oxidation state, and this is also a homoleptic complex composed of only one kind of ligand. How to name the one? First of all, start with the coordination number, go with the ligand, then with the metal, and then its oxidation state. Oxidation state is 0. So write down its name 4. So it is tetra. What is the name of the ligand? Carbon monoxide. It is a neutral. So it has its specific name, carbonyl. So tetracarbonyl. Nickel, whose oxidation state is 0. That's all. Let us name this complex. It is -1, so the counter charge of the complex will be +1. So from this information we can identify what is the oxidation state of iron. So chloride minus ligand 2 into -1, that makes -2. Nitrosyl 0, water 0, because both of them are neutral ligands. Now this is +1, this is -2, so I can write x minus 2 equal to +1 or x equal to +3. Therefore, oxidation state of iron in this complex is 3. So let us write the name. Cationic complex is first, so we have to follow alphabetic order because it is a heteroleptic complex. Chloride, nitrosyl, aqua. So A comes first. So let us write first of all water, followed by chloride, followed by nitrosyl. So how many times water is there? 3 times. So the name is triaqua. Okay. Followed by chloride. How many times there? 2 times. Triaqua dichlorido. because of negative ligand. O is the suffix. Then NO, it is a nitrosyl. So chlorido-nitrosyl. What is the central ion? Ferrate, sorry, iron, because of complex, positive complex, it is iron. So I can write iron. What about its oxidation state? 3, iron 3. That's all. The next one, once again we have the heteroleptic complex. Though the complex is anion, it has no counter ion. So how to name this compound? So here we can go with this oxalate, it is chloride, both of them are negative ligands. So we should find out what is the oxidation state of cobalt. Chloride -1, oxalate -2 because it is a didentate ligand. So I can write 2 into -2 plus 2 into -1 equal to -2 x plus, or x equal to 2 2s are 4 -4 -6, sorry, this is -3. So I can write -3 plus 6 equal to +3. Therefore oxidation state of cobalt is +3. Now let us write its name. Once again IUPAC name following that alphabetic order for the heteroleptic complexes. Chloride followed by oxalate. So the name of the complex is dichlorido, negative ligand, so it is chlorido. Oxalate also negative ligand. How many times I have? 2 times. So dioxalato. Cobalt, anionic complex. So cobalt ends with the suffix of ate, cobaltate. With the oxidation state 3. As it has no any counter ion, it ends with ion. So when the complex doesn't find of its simple counter ion, then the complex always ends with ionic. That means it specifies the complex in its ionic state. Okay. Next one, how to name the complexes having ambidentate ligands. So in this case, I have taken the complex of the type platinum NH3 twice Cl NO2. The other case, cobalt En twice Cl ONO with the positive charge. So this is, it bears the charge, so it is a cationic complex. Here we should find whether it is a neutral or it has any charge and all. So chloride -1, NO2 -1. So if at all it is 2, then the charge of the complex will be 0. As the complex has no charge, then it is taken as 0, neutral complex. Okay, let us write the IUPAC name of this complex. Heteroleptic, different ligand, so follow the alphabetic order. First it comes amine because of A, followed by chlorido, followed by nitrito. Okay, this NO2 and ONO are ambidentate ligands where I have taken NO2. So that means the nitrogen is the donor side to the platinum. Here ONO I have given. So the oxygen is the donor site of nitrito to the cobalt. So how to specify the donor site of ambidentate ligands in its IUPAC name? Let us write first of all diamine. So this is diamine. Then chlorido, diamine chlorido because of its negative ligand. And it is nitrito because NO2 is there, it is nitrito, nitrite group into nitrito. Then you have to write N like this. Then you should follow the metal platinum, platinum with the oxidation state 2. So here this N represents the donor site of nitrito is the nitrogen atom. Or else you can write such a way N platinum. So when you write this way, no need to make a hyphen between the N and the metal. Or if you don't write that symbol of K, you have to make the hyphen in between of the metal and the ligand as well as the donor atom, right? So here you can write this one. This is a cationic complex, so cobalt only. Find out the oxidation state of cobalt. This is -1, this is -1, this is 0. So if it is +3, 3 minus 2 becomes equal to +1. So let us write its name. Once again, follow the alphabetic order. Chlorido followed by nitrito, chlorido followed by ethane 1,2 diamine followed by nitrito. So let us write the first one, chlorido. It is a didentate ligand as well as it is diamine. So the 2 is taken as bis. Open the bracket in which ethane 1,2 diamine. Then it is nitrito. And which atom is the donor side to the cobalt? Oxygen. So write O with cobalt along its oxidation state 3. Instead of this, you can write even like this. Chlorido, bis, ethane 1,2 diamine, nitrito, KO cobalt 3. This is also correct. Okay. So that's all how to name the coordination compounds. So this is the way we have to follow to name the complex compound according to IUPAC system. Here some of the ligands and its charges as well as the donor site is given for the reference. Besides that, some metals and its common oxidation states also given. This is just for reference only. Besides that, we have so many number of ligands as well as the central metal ions we have. But at the same time, when you go this one, at least you will be confident about the charge carried by the anions and the charge carried by the cations. And neutral ligands, the name if you know, you can find out those charges will be 0. And in this part, all of these ligands are unidentate ligands alone. And in these negative charges, what you have to do, the letter E will be dropped by O, because I have given name of the ions only, anionic names only given. When these anions goes to ligand where it has to be end with the suffix of O, that you have to take care of that. And some of the cationic ligands are there. Here I have given nitrosonium and nitronium alone. And the rest, these are neutral ligands. So in all these cases, these are all unidentate only. This side I have given some multidentate. So some of them are didentate ligand and one of it is hexadentate ligand, that is EDTA. The formula is also given. Even better, you can refer with your reader. But the reason for giving this is, you should remember, you should know about the charge carried by the ion. This will be helpful to find out the oxidation state of the central metal ion as well as the charge of the complex. And some of the metals and its probable oxidation state is given, because the metal that can exist variable oxidation state particular to transition element. So silver and mercury probably in +1 state, and the mercury that can have even the +2 state also. And the di-positive ions are copper, iron, zinc, nickel, platinum, manganese, mercury. And the tri-positive mostly ferric, cobaltic, CO3+, chromium 3+, and Au3+. And tetra positive ion is platinum 4+. So based on these metal ions only, you will get most of the complexes. So you can remember probable positive oxidation state of the metal, but anyhow you have to find out, you have to confirm exactly the charge carried by the metal ion. Okay students, hoping that you will understand the nomenclature of complex compounds. Let us close our today's session and we will continue the same chapter in our following sessions. Until then, bye bye.